In this video, we'll talk about the process of convolution. We'll introduce the concept and we'll derive the convolution integral equation. Convolution is very simply a method for combining two signals. You could think of adding two signals or multiplying two signals. This is just another operation that you can perform on two signals. And there's a lot of ways we can interpret it, but for now we're going to think about convolving some signal x of t with the impulse response of the some system. Okay, so let's say we have a system that is, we know what the system is. Okay, so let's say we have some system, and let's say we know its impulse response. So let's say its impulse response, I don't know, we'll just give it some kind of arbitrary shape like that. Again, every system will have its own system response. And what we want to do is we want to combine the impulse response h of t and the input signal x of t to predict the system output y of t. Note that up until now, the only way we've had to do this is to take the Fourier transform of x, multiply that, perform a complex multiplication with the system's transfer function, h of j omega, and then that will give us the Fourier transform of the output signal y. If we want to see the time representation of y, we can reconstruct y out of cosines. But that's a frequency-based analysis. So what convolution lets you do is it lets you predict the same signal y, the same function output y of t, except it'll allow us to arrive there by doing a time-based analysis instead of a frequency-based analysis. So before we dive into that, let's just remember what we learned in the impulse response video. In the impulse response video, we learned that if you take an impulse, delta of t, and pass it into a system, you will get as output the system response h of t. Now, if that's true, by the linear time invariant properties of systems, if we were to take that same impulse and delay it by t sub d, okay, let's let t sub d stand for, the d stands for delay. So let's say this is delta of t delayed by t sub d seconds. Common sense would dictate that the output function should be that same impulse response but delayed by t sub d seconds. So this should be the same impulse response h of t but delayed by t sub d seconds. So if you delay the input, you delay the output by the same amount. That's one of the key properties of linear time invariant systems. The other thing that stands to reason is that if I make an impulse that's twice as big or 3 times as big as my original impulse, so let's say this is something like k times delta of t minus t delay. So if I make my impulse bigger by some scale factor, it also stands to reason that my output will be my same impulse response but scaled by that same factor. So this I would expect to be that same scalar constant k times delta of t minus t delay. Okay, so this is basically the time invariance property at work, and this is the linear property at work. Right? Linear means if you double the input, you double the output. Now, let's take that and let's go back to our input signal x of t. And what we're going to do is we're going to imagine that our input signal x of t is really constructed out of an infinite series of impulses. Okay? In theory, I'm drawing just a handful of the impulses, but in reality we know that there's an infinite number of these impulses packed infinitely closely together. And altogether they comprise signal x of t. So let's introduce a dummy variable, and I'm going to introduce the dummy variable tau. So let's say tau represents some point in time. Okay? Now, for this particular value of tau that I've shown on the paper, I think we can agree that the value of the function here, x of t, should be x evaluated at time tau. Okay, so the height of that, right, the y value of that point is x of time tau. That tells you how tall the impulse is at that point. So if I showed you just that impulse and I said, what is the impulse response in response to just that impulse, you would be correct to assume that the response would be h, the impulse response, delayed by tau, the same way that this impulse is delayed by tau, and it should be scaled by however big x is at that point in time. So if x has a really big value, that particular impulse response will be big. And if x has a small value, then that particular impulse response will be small. Okay? Now, we're going to repeat this process over and over again. Okay, I'm going to have all these impulse responses, and some of them are going to be bigger because the input function is bigger at that point. And some of them are going to be smaller because the input function gets smaller. So in essence, what I'm trying to do, whatever this the shape of that red curve is, I'm trying to replicate that here, perhaps a little inartfully. Okay, and then I'm going to add together all those impulse responses. Now, when you have an infinite number of something and you add them all together, really what you're doing is you're integrating. So what I'm going to do is I'm going to take this scaled and shifted impulse responses, and I'm not just going to accept it. I'm not just going to look at that over one value of tau. I'm going to look at that over all values of tau. I'm going to use little values of tau. I'm going to use big values of tau. I'm going to let all values of tau be a possibility. And when I put it all together, I get y of t. And this is the famous and much feared convolution integral. Okay, in the next few lectures, we're going to learn how to apply this integral and to think about it a little bit intuitively. And what we're going to find is that in a lot of cases, you're going to be able to predict the system output using convolution, but without actually having to crunch the integral itself. But that's where the integral comes from.